way how atoms interact determines the structure of molecules and crystals. And when we go to lower and lower temperatures, those structures are the ones that are the minimum of the potential energy. This is so according to classical physics. In quantum physics, however, we have some kind of undeterminism of the momentum and position of all the atoms. This is a so-called uncertainty principle, one of the fundamental concepts of quantum physics that was formulated exactly 100 years ago. So you may expect that due to this uncertainty, that is in other words the quantum fluctuations, the structure of all these molecules and crystals is to some degree washed out and smeared out. But for some materials, these quantum fluctuations can have much more dramatic consequences and can lead to very striking effects. For example, superconductivity or superfluidity. So the general question is, how can we really measure those fluctuations when they involve collective movements of several atoms?
So this is the reaction microscope end station of the SQS instrument. And the setup is designed to measure one single isolated molecule and to shoot this with one of our intense, very short X-ray pulses. And in order to be able to do this, what we need to do is first we need to achieve an extremely high vacuum in the experimental chamber, because we need to make sure that we don't shoot any unwanted molecules. And in order to do this, what we actually do is before the experiment, we heat up this entire setup to more than 100 degrees. And we keep it like this for 2 weeks. And this is actually why you see all this aluminum foil here. This is for insulation. So then our X-ray pulse will come from over here and will shoot one single isolated molecule, such as this one. And then this results in stripping off many of the electrons from the molecule, and the resulting positively charged atoms will then repel each other and then finally explode. And the exploding ions, we collect them on our detector, so we apply a high electric field inside, and this electric field smashes the ions onto the detector, where we collect the velocities and the types of ions.
So we get one molecule and we blow it up, and then we measure the fragments, and from that we try to know something about what the molecule was at the beginning before it exploded. Now, one problem we got with this molecule is that it's a bit too big, it's quite large, and we cannot measure everything in one go every time we explode one. So what we do is that we repeat the explosion hundreds of thousands of times, and then we put back together all the data. It's not so easy to do it, and in fact we had to develop a whole new analysis technique to achieve that. But when we do it, we can actually get a lot of information, a lot of very good information, even of some things as subtle as this tiny quantum fluctuation.
In our study, we managed to measure the quantum fluctuations in a complex molecule. In particular, we imaged the collective character of these fluctuations spreading over all 11 atoms of our targeted deuterium molecule. The existence of ground state quantum fluctuations has been shown, of course, already earlier, but examining that correlated behavior directly, I think that is beyond what was achieved so far. So we really obtain snapshots where we see that if we catch one atom fluctuating in a certain direction, the other atoms react to that in a specific pattern, and we catch them fluctuating in other distinct directions. So again, this collective behavior is theoretically, of course, well understood, but techniques to measure it have so far been limited basically to molecules consisting of 2 to 3 atoms. So I think our achievement is actually twofold. We observed this intriguing collective quantum phenomenon, and we really pushed the frontier of the Coulomb explosion imaging technique by developing new measurement and data analysis concepts. And I have to admit, in the end, all this worked out as well, thanks to the properties of the X-rays provided by the European XFEL. So where do we go from here? Well, what is next? Well, our work is of course still ongoing. The Coulomb explosion imaging approach is still far away from mature or from being a routinely applicable measurement technique. So we will have to work on that. We are now at a stage where we can handle molecules with the size of iodopyridine on a level that we can image the quantum fluctuations of the atoms of this molecule. We are as well able to perform first time resolved measurements. So we are able to shoot first movies of photochemical reactions going on in such molecules. To reach this point, we needed to develop new tools and theoretical models that enabled us to actually handle this huge amount of information that we obtain in our experiments. But of course, we want to go further. So far, we imaged the dynamics of the atoms, but at some point, we will start to image in addition the dynamics of electrons. The ultimate goal is to examine both at the same time, the femtosecond regime of the nuclei together with the attosecond domain of electron dynamics, and to learn how these two are interconnected. Conceptually, I think our measurement technique is actually able to do this.